Welcome back. Continuing. Let A and B be M by N matrices. Then A is row equivalent to B if and only if there exist elementary matrices even through EK such that B is obtained from A by sequence of multiplications by elementary row operations on the left, or if you are using column operations, then you have to multiply A by a sequence of elementary matrices on the right. The point is, if you apply say 5 row operations on A, then B will be obtained from A by multiplying by 5 elementary matrices on the left of A. How do you obtain these elementary operations, matrices? You take your identity matrix, whichever operation you conduct on A, do the same thing on the identity to get the first one. Whichever second row operation you conduct on A, do the same second operation, row operation on identity to get E2. Likewise, keep going. If A is row equivalent to B, then B is a result of a sequence of elementary row operations on A. That's what it means to be row equivalent. From the previous theorem, we see that B has to be therefore left multiplied by a sequence of elementary matrices on A. Sorry. Notice this is if and only if. So you started with one direction. Let's go to the reverse direction. If B is obtained from A by multiplying a sequence of elementary matrices, well, again by the previous theorem, it just means you are doing elementary row operations on A. Whichever row operation E1 brings, that's what is applied to A. After E1, whatever operation E2 brings, that's what is applied to the result, and so on. So B is obtained by elementary row operations on A, which means B and A are row equivalent. Okay? Next theorem. An elementary matrix E is non-singular. Every elementary matrix E is non-singular. Moreover, its inverse is an elementary matrix of the same type. So, let E be an elementary matrix of type 1. What does that mean? You take identity matrix, interchange row I and row J. That's what EI is. Note, another interchange of rows I and J will result in I again, you see. I hope it's clear. I interchange two rows. Pretend I have interchanged row 3 and row 4. Well, I interchange them again. Then you get the identity back. That's all we are saying. E is that matrix which you get by interchanging row I and row J. Apply E again, you get back identity. E times E is identity, which means the inverse of E is E. In other words, E is not only non-singular, its inverse is the same type. This was type 1. Now suppose E is elementary matrix of type 2. What does that mean? E is obtained from identity matrix by multiplying the ith row by some number A, non-zero number A. Because A is non-zero, I can also divide by A. So whatever result you get, on the same row, divide by A. You get back identity. You see? So the inverse of this A is the same type, type 2, multiplication of a row by a non-zero element. Suppose E is elementary matrix of type 3. What does that mean? E is obtained from identity matrix by multiplying ith row by A and adding to jth row. Okay? Multiply ith row of by A added to jth row. That's your E. Well, if I can add, I can also subtract. Multiply ith row by negative A added to J. That will get back your identity matrix. In other words, inverse of E is of the same type, type 3. Here is a lemma. Lemma means a small result. Let A be an n by n matrix and let the homogeneous system Ax equals 0 have only the trivial solution x equals 0. Okay, so Ax equals 0 only has x equals 0 as the only solution. Then A is row equivalent to identity. What does that mean? You can make elementary row operations on A and get to identity. How is that possible? Let's see. Suppose B is the reduced row echelon form of A. Okay, B is the reduced row echelon form of A. Every matrix can be reduced to a reduced row echelon form. What does that mean? You have conducted series of operations on A. So B and A are equivalent. So Bx equals 0 and Ax equals 0 are equivalent. That is, they have the same set of solutions. B is also size n by n. So we don't know much about B. All we know is that it is reduced row echelon form. So there should be some non-zero elements. If there are any non-zero rows in B, then that number R, that is number of non-zero rows, has to be less equals n, because B has in all n rows. So the number of non-zero rows has to be less equals n. On the other hand, these two are equivalent systems and A has only 0 as the solution. So Bx equals 0 also has only x equals 0 as the only solution. Which means number of variables has to be less equals the number of non-zero rows. You see, if you had more variables than the number of non-zero rows, imagine the picture. You have more variables than the number of non-zero rows. Then the row reduced echelon form will have bunch of ones, and there are more variables. So something more on the right hand side, something non-zero on the right hand side. Which means you will have non-zero solutions, right? So number of variables cannot be more than number of non-zero rows. In other words, number of variables has to be less equals. So compare this, R less than equals n less than equals. How is that even possible? The only way it is possible is when n equals r. N equals r. So our matrix B, that is the reduced row echelon form, is size n by n with n number of non-zero rows. So imagine a reduced row echelon form, a square matrix, and the number of non-zero rows are n. Well, the only way that is possible is B is identity. Which brings us to the conclusion. A is row equivalent to identity because A was row equivalent to B. Okay. Which brings us to a theorem, an important theorem. Suppose A is non-singular. Sorry, not suppose. A is non-singular if and only if, so this is a two-way condition, A is a product of elementary matrices. Okay, from what we have seen so far, this should follow straightforward. One direction. Suppose A is a product of elementary matrices. So we are assuming the latter, the statement. We want to show that A is non-singular. A is a product of elementary, of non-zero non-singular matrices because elementary matrices are non-singular. We just saw every elementary matrix is invertible or non-singular. If A is a product of elementary matrices, then A is a product of non-singular matrices. Well, product of non-singular matrices is non-singular. Therefore, A is non-singular. So you started from the second statement and concluded the first statement. Conversely, suppose A is non-singular. Then consider the system AX equals 0. Use elementary row operations. We can convert it to Bx equals 0, where B is the identity matrix we just saw in our previous lemma. That is, B is identity, which in turn is a bunch of elementary matrices added to A on the left. Okay? B is all of this. So what do I do? I take E1 through ER, write its product inverse, I equals A. So I'm looking at the second equation. So I take this entire mess, put it in parentheses. We know they are elementary, so they are non-singular. So the product is non-singular. Take its inverse, multiply it to I on both sides. So only this equation. Okay. Multiply to the left by that, you get this, equals multiplied on the left by that, you get this. Okay, look at this. What happened here? This quantity is inverse of this quantity. So they cancel each other. You are left with A. On the other hand, you are multiplied by this to identity. So that's that. Notice inverse reverses order, product of inverse of a product, you have reversed order. But if you remember, inverse of elementary matrix is also elementary. Okay, inverse of elementary matrices are elementary, and we have just shown A is a product of elementary matrices, which proved the theorem. Corollary. Corollary is something that follows. A is non-singular if and only if A is row equivalent to identity matrix. That is, reduced row echelon form of A is identity. You are non-singular if and only. Okay. So let's go back. Non-singular if and only if A is a product of elementary matrices. Now you are saying non-singular if and only if A is row equivalent to the identity. That is, the reduced row echelon form of A is identity. We know A is row equivalent to identity. That's what, that's the second statement. Assume A is row equivalent. What does that mean? You are taking some elementary operations on A and you're getting IN. Okay, that's what it means to be row equivalent. Take elementary operations on A, you get IN. Elementary row operations is nothing but multiplications on the left by elementary matrices. So a bunch of things times A is identity. What does that mean? The inverse of A is all of these things. Again, remember, inverse of a product reverses order. So E1 inverse, E2 inverse, EK inverse. Okay, notice the order has been reversed. Therefore, A is non-singular. Let's continue the converse in our next video.